Okay, so today's learning objective is to compare lengths, areas, and volumes using ratio notation. Make links to similarity, including trigonometric ratios and scale factors. So we've kind of done, at least the first part of this already, in the sense that we've been comparing, we've been using ratio notation for a while now. But the thing is, you have to apply this to a certain circumstance or a certain context. And the context they're talking about is saying, if you have for example, a square, right, and you have to compare the ratio of, say, the what is this called, the length to the width. So if this was, say, 5 centimeters, this was 10, you could say the ratio of the length to the width would be 5 to 10, and you can simplify this to 1 to 2. So that's kind of what it is. Or perhaps if you have, say, the volume of one box, one poorly drawn box, very poorly drawn box is, say, 50 centimeter cubed. The volume of another one is, say, 100 centimeter cubed. Again, you could do volume of one box to the volume of A to volume of B. So let's call this A, let's call this B. It would be, again, 50 to 100, and you can again simplify this to 1 to 2. So that's what it means comparing lengths, areas, and volumes using ratio notation. And then make links to similarity. So this is what similarity basically means. If we have, say, a square, or let's say actually a rectangle that's kind of 1 meter, let's say 1 meter thick, or sorry, wide, and 2 meters long, right? And we have another rectangle that's 2 meters long and then 4 meters wide. So again, 2 to 4. Basically, if you can kind of tell that this rectangle is just kind of, if you stretch it, if you pull it out, basically, you'd have it, say, like a zoom function or something. Or actually not. Why don't we use right? So you have this rectangle, right? And if you take this same rectangle and you just kind of pull it out like this, you've got the rectangle on the right. So this is what it means by similarity. Basically, the rectangle on the right is just an enlargement of the rectangle on the left, and the ratio of the of the length to the width is the same. So saying, length to width in this one is 2 to 1, and here it's 4 to 2. But 4 to 2, and that can simplify to 2 to 1. So because the ratio is this of the length and the width are the same, basically, kind of one of them is just kind of, if you enlarge it or kind of if you pull it out, basically, on a, like as I showed here, it's like one is another one of that. So one's an enlargement of another, basically. And because of that, there's some useful properties that come from this. That when this ratio, for example, holds for a rectangle, we say that they're mathematically similar. That's kind of just the definition, that the ratio of these length to width is the same. For, say, if we were to deal with like a cube, not a cube, maybe say like a cuboid, actually. I'm going to be pretty bad at drawing these, but so basically, for a cuboid to be kind of mathematically similar to another, the ratio of its, say, length to width to height, is the same as the ratio of kind of another larger one. So again, you've taken like a box and you kind of just enlarged it, and if the ratio of the length to width to the height stays the same, then again those cuboids are mathematically similar. And this can again apply to, say, a cylinder, for example. If the ratio for a cylinder, what we're concerned is kind of the radius of the circle at the bottom and the height. If kind of, say, the ratio of, sorry, the height, that's not the height. The height. So the ratio of the radius to the height is the same as another cylinder. That means, again, they're mathematically similar. So basically, you think of kind of the important kind of lengths of an object, for example. So if it's a 3D object, you think of kind of what lengths you measure. So for a cylinder, you measure the radius and you might measure the height, and that's all you need to know. That's kind of what the cylinder looks like. Whereas with a cuboid, you need to know length, width, and height to know what the cuboid looks like. So once you have those three, and kind of if you have a ratio for those, and another object has the same ratio of those kind of important factors or important lengths, it's mathematically similar. Again, kind of same logic with rectangles. So if we had, say, triangles as well, if the ratio of the three sides was the same, then we could say it's mathematically similar to another triangle. So knowing that, that's what mathematical similarity is, and there's a kind of this interesting property that comes with it, is if we can see in questions like this, right? So solid A and B are mathematically similar. The ratio of the height of solid A to the height of solid B is 3 to 4, and the surface area of solid B is 96 centimeters squared. Calculate the surface area of solid A. Okay, so basically, if we think about solid A, let's pretend like it's a box, right? We've got a box, badly drawn box, and then we've also got, can I select all of this? Yeah. And we've got another box, but it's just larger. That's because we know solid A and B are mathematically similar. A and B are mathematically similar. And we also know that because that the ratio of the height of solid A to solid B is 3 to 4. So solid A, kind of the height is, say, x, and the height of solid B is 4 over 3x, right? From the ratio, we know that. And we also know, because that, the kind of the ratio of, say, if we label the lengths x, y, and z, right? We know x to y to z, the ratio here is the same as the x to y to z ratio here. And for that kind of ratio to work, for the ratio of x to y to z to be the same, if x is if you multiply this by 4 over 3, you have to multiply this by 4 over 3, so this becomes 4 over 3z, and the height becomes 4 over 3y. Sorry, 4 over 3, and then not the height, I mean what's called the width. So, because again, just to quick recap, the logic here is that we know that the ratio of the x to y to z is the same, and we also know that kind of if this is x, this is 4 over 3x. And the only way we can maintain the same ratio is if this becomes 4 over 3z and this becomes 4 over 3y. And now we know that, right? We need to calculate what the surface area is, okay, of solid B. There's kind of one way we might think about this is, right, what's the surface area of solid A? So the surface area of solid A, it's xy plus xy. Sorry, so this it's 2xy plus 2xz plus 2zy. You can that's kind of a formula you might have seen before, and you can kind of work through each kind of phase to figure out why that works. So it's 2xy plus 2zx plus 2zy. For a surface area of A. If we look at the surface area of B, is equal to 2 times by, so its x, kind of its length basically, its height times by its width, so 2 times by 4 over 3x times by 4 over 3y plus 2 times by 4 over 3x times by 4 over 3z plus 2 times by 4 over 3z times by 4 over 3y. And if you actually look at what this is just 4 over 3 squared times by what the surface area of A, 2xy. If we just take 4 over 3 squared out from this one and this one and this one, we just get 4 over 3 squared times by 2xy plus 2zx plus 2zy, which is just kind of the surface area of A, right? Times by SA of A. And basically, the kind of the trick here is that if we know kind of the ratio of the heights, for example, then the ratio of the lengths is whatever between solid B and A, right? So let's say the ratio is A to B, right? For areas, it will be A squared to B squared, and volume will be A cubed to B cubed. Because you can see why for surface area, for example, surface area is when you multiply one length by another length, so kind of length by width or length by height or whatever, right? And since there's 2 of those, and each of those has kind of been multiplied by 4 over 3, you get the 4 over 3 squared. So this is the quick trick. So if you know the ratio of, say, the height is, the heights or the widths or the lengths, i.e. kind of one thing, it's one length basically, you know what that is, then you know that for the areas it will be that squared, and for the volumes it will be that cubed, because you kind of use that, that thing 3 times over in the volume case and 2 times over in the area case. So now you have that. Going back to this, we know the SA of B is 96 centimeters squared is equal to 4 over 3 squared times by SA of A. If we divide both sides by 4 over 3 squared, we get 96. 96 times by 3 over 4 squared, which is equal to, using a calculator, 96 times by 3 squared over 4 squared, 54, and that's our answer. 54 centimeters squared, not to forget the units. Okay, moving on to another question. Solid A and B are mathematically similar, so again, similar principle to before. The volume of solid A is 18 centimeters cubed, and the volume of solid B is 1152 cubed. Calculate the ratio of the height of solid A to the ratio of the height of solid B. Okay, so again, we know if the ratio of the volume A to volume B is something, we know or actually let's talk about this in reverse. If we know the ratio of the lengths is, so length of A to length of B, and when I say length, I don't mean explicitly say kind of this, whatever would you call it, the length here, I mean kind of length, width, or height, because any kind of single unit, right? So it's because this is, you can measure length on, let's say, a ruler, right? You just measure length, but you just measure that straight away, so that's a length. Same thing with the width, you just measure it with a ruler, right? With area, you have to use 2 numbers and multiply them together, but length you can measure directly with a ruler. So because you can do that, that's kind of, these are basically like these single things, right? They're just, lengths are, for example, just in meters, right? Whereas area is in meters squared, and volume is in meter cubed. And now I'm thinking kind of, when I say length, I mean anything that's measured in meters. So if we know the length of A to the ratio of that, we know volume is that cubed, as I talked about before. It'd be kind of, it's that cubed to that. So if we know for volume, if the ratio of length of A to length of B is, say, x to y, then for volume, it will be x cubed to y cubed. In this case, we have the volume case. We have that x cubed and x cubed to y cubed basically is 18 to 1152. So if we take a cube root of both sides, we should get the x to y ratio. So taking the cube root of 18, cube root of 18 is 2.62. Let's see. And the cube root of 1152. So basically you get, so I've seen that on the calculator, I don't get nice numbers, and that's not usually what's supposed to happen. So in fact, if we do what the cube root of, kind of think about what the cube root of 18 is equal to, right? 18, the cube root of 18, well, we know 9 times 9 is 18, right? So that's kind of, 18 is the same as saying, well actually, let's simplify this ratio first, so that might make our lives easier. So 18 is clearly divisible by 3. 1152 is also divisible by 3. So dividing both sides by 3, 384 to 9. And I think 384 is also divisible by 3. So 128. And 128 is not divisible by 3. Now if we take the cube root of both sides, cube root of 3 is just cube root of 3 to cube root of 128. Is 5 point something. Ooh, okay. So I guess we don't get nice numbers in this case. Oh, I made a mistake here. So 18 divided by 3 is not 9. So in fact, if we kind of just go back to where I was, sorry for those mistakes. So, just kind of as a learning thing, sometimes when you get ugly numbers, you might want to go check back, to see if you were doing the right thing, and I realized I spotted a mistake there. So, I realized 1152 is actually divisible by 18, so dividing both sides by 18, 1152 divided by 18, So 1 is 64. And if we take the cube root of both sides, that's 1 to 4. So the ratio, so kind of, therefore, the ratio of heights is 1 to 4. So height, and they've asked us of height A to height B, and we've got, we've done volume A to volume B, so that's correct. So it's in this order, so it's 1 to 4, that's our answer. Hopefully that all made sense in this video. There was a bit talked about in this video. Kind of the key thing to remember is if the if the ratio of the height, or so anything measured in meters, so that's why I say length. So length, width, or height. So I'm just going to say length. Right? If the ratio of lengths is length to length is x to y, then ratio of the areas will be x squared to y squared. It doesn't matter if this is area or surface area. As long as the word's area in it, you can kind of do the x squared to y squared. And for volume, it will be x cubed to y cubed. And once you have this, you can always go from ratio of volumes to lengths, and then volume to area or whatever, right? So if they gave you the ratio of the volumes and asked you to calculate the ratio of the areas, you could kind of go back to lengths and then to areas, for example. So as long as you remember this kind of principle, that hopefully kind of explains why that works. And of course, this is only the case for mathematically similar ones, right? So for mathematically similar ones, not for every case, but for these, this kind of holds. Hopefully that all made sense, and I'll see you guys.